Good morning, Professor. My name is Pavli and I am from Team 20. So today I'm going to talk about my research project, which is called Real-Time Sign Language Detection using CNN. CNN is Convolution Neural Network. This is one of the deep learning technique that I have used to in this project. So first I would like to talk about the abstract. So sign language recognition has generally plays a crucial role in bridging the communication barriers for the ordinary people and also the people with the silent and the deaf. So it is like a communication barrier for it. So sign language generally relies on hand gestures, facial expressions, and body languages, which will convey the meaning to the other people. So many researches have been done in the sign language recognition, like different types of sign languages have been done. So, and there are also got the many difficulties, which includes the training the lengthy periods for deep neural networks like CNN, RNN. There are other couple of techniques that are also available. And also, it requires the very large data sets for training the model, like millions of photos it requires. So, therefore, to solve this problem of training a very large data set, which takes a lot of time, so in this paper, I have used a technique called transfer learning approach, in which we would take a pre-trained model as we have got many pre-trained models like which are already trained and highly accurate model. So we will take that and adjust. I have taken that and adjusted the parameters according to the final layer with our task. So what happens is thereby it reduces the training time and also it requires very small set of data like very less than 10 images per gesture. So if the data is very limited, if you're able to access a very limited data, this approach will be very much useful. Next, I would go with the introduction part. So, in human life, the communication has been a very fundamental and effective way of sharing thoughts and opinions. So there are about 72 million deaf and silent people on the globe, according to the survey. So every time there is a communication gap between the deaf, mute individuals and the ordinary people. So the unique language based on the hand gestures and facial expressions has been discovered, which is nothing but the sign language. So we have different types of sign languages like Indian, Arabic, American. According to their native and region languages, we have got different types which are already been discovered. So communication through these sign language composes of postures and gestures, which is quite close to human PC association. So the recognition of this communication through sign language is divided into two classification. First one is the vision based and the second one is the sensor based. So in vision based approach, the features corresponding to the palms, finger positions are estimated, which are then used to perform the recognition. This method it requires acquiring images from the webcam or through camera using the image processing techniques. I believe I have used the same one right now in this paper. And in the sensor based, what happens is wearing a glove with electromechanical gadgets into usable information. It's a primary kind of data glove technique. So this approach has a downside, which requires the utilization of extra gear and yielding discoveries that are less extract. So in recent years, the researchers have employed the deep learning for sign language recognition systems, so which involves various methodologies and data sets. At ultimately, it aims to improve the accuracy of the system. So in this paper, I'm using the CNN technique for recognition and also aiming to achieve high accuracy with very small data sets in which I am taking only 5 images. For each image, I'm taking again 5 images, which is like a 20, approximately 25 images by leveraging the transfer learning approach. So the main goal of this project is to create a real-time sign language detection using the TensorFlow Object Detection API, which is an open source API, which offers the instant and precise interpretation of the sign language gestures for each detection. Next, I would talk about the related works, like the previous works that has been done in this particular a particular project. So, researchers have been studying the sign language for years and they're attempting to improve the model by using various techniques. So, most of the common deep learning techniques that have been used for recognitions are k nearest number, support vector machines, hidden Markov model, and convolution neural networks. So these are the most common learning techniques that are used for the recognition. So generally for KNN and SVM, it requires very large data sets to achieve its maximum prediction accuracy, whereas HNN, HMM and convolution neural networks requires a lot of training data to achieve the good accuracy. So as I'm taking here the CNN and I don't require the most of the training data because already I'm taking a pre-trained model. So this is one extra thing that I have done by using the transfer learning approach. There are again many deep learning techniques that have been used in the past years. So next I will go with the methodology of the project. So deep learning is nothing but a subset of machine learning which utilizes artificial neural networks with multiple layers of connectivity and also enables the automatic extraction of hierarchical features from the data. So overall, deep learning's ability to automatically learn the hierarchical representations of the data has succeeded in various fields, including the natural language processing and computer vision. By leveraging the power of the artificial neural networks with multiple layers, deep learning have unlocked new opportunities which solves complex problems. So here in this, I'm using a transfer learning approach, which is a fundamental concept in deep learning. It involves leveraging the pre-trained models, which are trained on the large data sets, and fine-tuning them for specific tasks is the key component of this proposed methods. Unlike the traditional methods, like um, unlike the traditional methods where I have to do it everything from the scratch, especially in the scenarios where only limited labeled data is accessible. So this is the I'm taking this approach where thinking only limited label data set is accessible. Whenever the people have very limited data, I think they can go for this approach. So next I would go with the model, which is the system architecture of the CNN model that I have taken, as I have taken the CNN as a deep learning technique in this project. So the overall architecture, I would say we can see in the figure. It composes of layered feature extraction module and the classification module. So in the feature extraction module, what happens is this module is responsible for extracting the relevant features from the images. So after the data augmentation is one of the image processing technique. So images are scaled and normalized to get the uniformity, and then they're fed into the convolution layers for feature extraction. So each convolution layer will be followed by a rectified linear unit. Then again, each convolution layer is followed by a max pooling layer. What max pooling layer does is which downsamples the previous feature map by half. Next comes a classification module. In this classification module, it accepts the feature map that is from the feature extraction um, and flattens it as a feature vector. Then the two fully connected layers, it densify the feature vector sequentially, and then the C-dimensional score is transformed to predict the output. So it predicts the output. And next we would see the system flowchart. So here it represents the system flowchart. It's nothing but the what are the steps that I'm going to do in this particular project, like how I am going to start. It is divided majorly into two phases. One is pre-processing phase and the detection phase. When we see the flow chart, first I'm trying to set up the environment in which I'm trying to set up the virtual environment where I can load all my files and folders in the virtual environment. And then I'm trying to collect the images using webcam. using the Python and OpenCV. OpenCV is nothing but it offers features primarily targeted at computer vision in real time. It is a standard architecture for computer vision based applications. So in this, what I'm trying to do is every image is captured and it is given a time of 5 seconds gap for each gesture. If I'm taking a five images for one gesture and I'm giving a 5 second gap and then taking another image. That's how I have collected all the images. And using the label image package, I have labeled all the images. So label image is an open source free program which graphically labels images. And once I save the file, they are saved as XML files, where when you open the XML files, it consists of details such as class type, bounding box configuration, number of pixels. It gives all those details in it. After that, I would so these are the steps that are involved in pre-processing phase and the detection phase. In pre-processing, we are collecting the images through the image pack, through the webcam by Python and the OpenCV, and also labeling images through the label image package, which is an open source free program. And again, after that, we are splitting the images into testing and training, which is like an 80 into 20 ratio, 80% of data in training and 20% testing. And when it comes to detection phase, we are generating the TF records. In this, we are trying to use a TensorFlow object detection API, which is an open source framework which makes it easier to develop, train, and deploy model. So here, two TF records are taken. One is for training and one is for testing. And we have also taken the pre-trained model, which is SSD Mobile Net V2 320 into 320. So we have taken this pre-trained model for the TensorFlow model Zoo. So the mobile net V2 SSD is a single shot multi-box detection, which performs the object detection by scanning images pixel that will be inside the bounding box coordinates and class probabilities. Next comes the training the model configuration. Pipeline configuration, which refers to setting up and updating the pre-trained model configuration, which is like when we take the pre-trained model, we have to update the model configuration according to our task, right? That is the pretty much the thing that I'm doing in the training the model configuration. And then training the model. This is executed with the Python script, which I will show you how I have done at the end, which makes use of the revised checkpoint where the updated or the last checkpoint will give the maximum prediction of it, and then detecting in real time. The testing image is fed into the model and then transformed it into 2D matrix, which is known as tensor, and then we'll get the image in the real time. The next is so these are the steps that are involved in the proposed method. These are pretty much this all the steps that are already there. So this is the extra step that I'm doing. I'm trying to download the pre-trained models from the TensorFlow Zoo, which is the SSD MobileNet V2 320 to 320. This is a model pre-trained model that I'm taking in this project, and I'm copying the model configuration to training and updating the configuration for transfer learning. So this is nothing but I'm updating according to my um, the project which I'm taking only five images and etc. and then training the model. So this is the pretty much about the transfer learning approach. Here comes the implementation. So the data set contains of the five signs, which I've already told hello, yes, no, thank you, and I love you. For each sign, I have taken five images, and I've also taken the dependencies, OpenCV, OS, time, and UUID. So this utilizes a transfer learning with MobileNet V2 architecture. As I've already told, the pre-trained model is SSD MobileNet. All the images in these datasets are compressed to 320 to 320, and then they're again converted to original resolution. So the advantage is no need to do anything from the scratch because we are taking a pre-trained model. So this is how the I have labeled the images using Python image package, which is label image. I have taken a portion of the image and then labeled it as hello. So as I have not taken the total image, I have taken only the portion like hello, thank you, yes, and etc. So these are the portion of the images that I have taken to label it. And what are the tools that I have used? So I've used a TensorFlow. TensorFlow is an open source artificial intelligence program which uses the data flow graphs to generate models. There are several layers of neural networks with this software. So the open source TensorFlow API for object detection is TensorFlow Object Detection API. And I've also used the OpenCV, which is used for solving the computer vision problems. Real-time applications requiring high level of computing efficiency and ability. It also has ability to handle large amounts of data. So these are the TensorFlow and the OpenCV are the two tools that I have used mainly in this project. Next, we'll see the experiments. So the model I have so the training of the model which involves the training and testing images and the label map file which contains the different types of classes defined. As I have told, I have given the labels to the images, which is like hello is the first image, no, yes is the second image, like that. So those are the label map file contains. And I have trained the model for 25 to 30 times, requiring 2000 steps to finish each epoch. The training determines how many steps are taken in each epoch. So in TensorFlow training process, what happens is whatever the safe TensorFlow models are obtained after a fixed number of iterations that are known as checkpoints. So after training the model for 2000 epochs, three checkpoints will be created, and the last checkpoint will have the highest accuracy of detection when compared to the previous checkpoints. And next we'll see, so this is the total loss that are incurred during the last part of the training. So I have got the localization loss, classification loss, and regularization loss. So these are the losses that are incurred. So total loss is nothing but the total loss is the overall error incurred by the model training. Localization loss is nothing but it measures the discrepancies between the predicted bounding box coordinates and the ground truth bounding box. And the classification loss is used in classification tasks. It measures the discrepancy between the predicted class probabilities and ground truth labels. And the regularization loss is nothing but it prevents the overfitting and improve the generalization ability. So I think I got the pretty much very less loss because the accuracy was high, so the loss was very less. And when you see that the loss evaluation metrics from the TensorBoard is also a graphical analysis tool where we can see all the graphical analysis. Here, when you see it was very high, and it lows down to 0.06, which is pretty much low loss. So these are the evaluation metrics from the TensorBoard tool. And now here I would like to show the code that I have executed in the Jupyter notebook. So if you see here, first I have installed the OpenCV Python and imported all the dependencies. And here I have labeled all the images. And each image I have taken 5 images, and also I have given paths to all the images. And here this is how I have collected images through webcam. So, and also given the time of sleep of 5, which means a 5 seconds gap for each gesture. And I've also installed a label image package. So this is how I've upgraded the label image package through Python. And I have labeled my images through the label image package, and then I have also given the paths to it. This is how I have done collecting and labeling the images. And then next I will go with the training part, training the model. I have imported all the custom models, and I have given all the paths to it and installed the TensorFlow object detection. And also I have verified the paths in which the detection has been done, which I have got the okay for it. And also I have taken the pre-trained model, which is SSD MobileNet. Here I've got the checkpoints. Actually, the pre-trained model first they have taken on the COCOS data set. This is what it resembles. And as I have already told, I have labeled the images like name,
hello as ID as 1, yes as 2, no as 3, like this. And here it has created the train record, test record, which means I have taken the training images and testing images. And here, as I have told the check about the checkpoint, so it will give the last checkpoint, which will get the more accuracy. For it, here it's the configuration, pipeline configuration, which I have explained before. And here I have taken the batch size as 4, and then the training script. And in this, if we go down, so these are the performance metrics, I would say, that I have got. And if you also see the loss localization classification model, so when we see here, I have taken the image path as test as hello. And when I go down and try to hit enter, and I would get the hello. And if I try to change this image to another image, um, it will also show the image which I am talking about. Let me take the I love you path, and I would like to show the difference of the images that I have done. So, yeah, if you see here, the image path is guarded as I love you. And if I try to do the See, if I say the I love you and the accuracy is 99%, this is a prediction score I was talking about. I can also show the thank you. This is the thank you JPG that I have given in this, which I have labeled it. I'm updating this thank you. See, thank you. I've got 97% as a prediction score. So this is pretty much the code that I
So this is the output code that I have shown from the Jupyter notebook, which I have included in the slides. So these are the code that I have executed in the Jupyter notebook. And next, I would talk about the Next, we would see the result. The accuracy is the accuracy that is obtained approximately for all the images is 99%. When you see only that for thank you, I got 97%. So as it has been obtained at the step 2000 on the testing image. So according to the table, the highest overall accuracy that I've got is the 99%. And next is the performance metrics that, as I have shown in the code. There are accuracy, recall, and the precision. Those are the performance metrics. So the effectiveness is evaluated using the performance measures only. How accurate is your model? So the true positive, true negative, false positive, and false negative. So accuracy, so true positive is nothing but the accurate true label is followed by a positive label. And the true negative is expected label is negative and the true label is accurate. And the false negative, false positive is genuine label is incorrectly reported while the expected label is positive. And the false negative is refers to a situation where the true label is inaccurately expected to be negative. So the accuracy, precision, and recalls are calculated from these measures. So the accuracy refers to ratio of correctly predicted instances, which are true positives and true negatives, by overall the all the divided by overall all the performance measures. And the precision is ratio of correct prediction over all the predicted values. And the recall is a ratio of correct prediction over all the predicted values that are to be positive. So these are the few performance metrics that I have calculated and showed in the project. And the next one would be discussion. So here I would like to discuss what about everything that I have done in this project.
So in this, I have examined the data processing, model training, and the evaluation phases. So as it has only two main phases, pre-processing is the first phase, and then which mostly setting up the necessary Python and TensorFlow environments. TensorFlow Object Detection API is an open source framework that is built out top on TensorFlow, which is nothing but training, deploying the object detection. So with the help of pre-trained model, computer vision can utilize the transfer learning strategy, which has saved time in my work. So as a result, I'm able to train the sign language detection model faster, and also I have obtained high average accuracies. And the conclusion and the further research, this can be extended with any number of images that you have, like custom, you can do it. I have restricted only to five. You want to restrict to five, you can do any number of images. And it can also be expand the data set to obtain the high accuracies. And this can also be used in further research by including techniques to increase the accuracy and integrated in different online video meetings like Zoom and the Google Meet for the deaf and mute people to interact to overcome the communication barriers. So in this paper overall, I have used real-time sign language based on transfer learning using MobileNet B2 as a pre-trained model. So as it has given a high accuracy with the transfer learning technique, I would like to say the transfer learning technique has helped to achieve the sign language recognition in the real-time application. Thank you so much. This is pretty much about the project.